Hello class, welcome to this video on the Cycle 3 midterm review. So we're going to go ahead and get started. For the first topic here, GR 1.3, we're looking at triangles and determining what the third side is going to be based on the first two sides. So here we got 5 inches and 22 inches for two sides of a triangle. What is the greatest possible measure of the third side? Remember that for the this is called the triangle inequality theorem. So it states that basically if I have a triangle with two sides A and B, then it states that the third side C is always going to be less than the sum of the two sides. So if I add A and B together, it should always be greater than the third side. So we have A plus B is always going to be greater than C. In addition, it also says that if I take the difference of A and B, so if I subtract A and B together, so if I do A minus B, I'm going to put absolute value just in case A is smaller than B, then this is always going to be less than C, less than the third side. So in other words, if I put these together, I can say that C has to be less than A minus B, but greater than A minus B, but less than A plus B. Okay, so C is between these two quantities. So this is the inequality. Okay, for this example, we have 22 minus 5 is less than, and we're going to call the third side x. So let's say the third side is x. Then x is between 22 minus 5 and then 22 plus 5. So we have here 17, x is between 17 and 27. So that means that the smallest, or the greatest possible side, the greatest value of x is going to be 26. Okay, that's the biggest that it can get before it stops being a triangle. All right, once it hits 27, it's no longer going to be able to form a triangle. Okay, so the greatest possible value is 26, and this is for it to be an integer. An integer is a whole number. For number 2, you're going to do the same thing. So we got 10 minus 8 is less than x is less than 10 plus 8. So we have x is between 2 and 18. So the smallest possible measure of the third side, the least value of x, is going to be 3. The smallest value of x is 3 because once it hits 2, it can no longer form a triangle. It has to be strictly between 2 and 18. So the answer is x equals 3. And here x equals 26. The sides of a triangle are 5 yards and 9 yards. Which of the following cannot be the measure of the third side? So x has to be between 9 plus 5, or between 9 minus 5 and 9 plus 5. So it's between 4 and 14. So x cannot be 4 and x cannot be 14. So the answer is 4 and 14 because it cannot be either of those. All right. So GR 1.4, so we're going to go ahead and, so for this one, this one's based off of parallelograms. Now, on here, for the second part, it says algebraic expression that represents the diagonals. I do not have a rectangle problem on here, so on this video, I'm going to do a bonus problem on a rectangle, okay? So I'm going to draw a rectangle, A, B, C, D, with two diagonals, and so this is a rectangle problem. So, and let's suppose that this is 5x minus 1, and then let's suppose that this here is 3x plus 8, or plus 9. We'll do plus 9 here. Okay, and then let's say we want to solve, or we want to find AC. Okay, so we'll do that problem later, so for this video there's a bonus problem, and that's going to be for a rectangle. All right, here, so we got a parallelogram here. So for this example, we know that a parallelogram, these two opposite angles are congruent, so we can go ahead and set these two angles equal. And we know that these two angles here are alternate interior angles because this is a parallelogram. So these are supposed to be parallel. So we got alternate interior angles. So we know that 1/4 x is equal to y minus 8. Now what I can do is I can solve for x, which is what I'm going to do here. I'm going to multiply by 4 on both sides. So when I do that, I get x equals, distribute the 4 times y, 4 times 8 is 32. And then I'm going to plug this into here, okay? And that'll help me convert that equation into an equation that's entirely consists of only y's instead of x's and y's. So if I plug that in, I get 4 times 4y minus 32 minus 8 equals 8y minus 12. So I'm going to distribute. We got 4 times 4. We got 4 times 32. We got 8y minus 12. Okay, so we're going to combine these like terms. I'm going to subtract 8y on both sides. I'm going to add 136 on both sides. That gives me 8y equals 124 divided by 8, which gives me y is 15.5. And then I got to make sure to plug this in here to get x. So I get x equals 4 times 15.5 minus 32, which is 30. Okay. So we got x equals 30, y equals 15.5. Okay, so for the next problem, so for the parallelogram, we know that adjacent sides, or two consecutive sides, the sides or the angles next to each other rather, are supplementary. So these two angles must add up to 180 degrees. So we can combine like terms. We got 5x plus 10 equals 180. Subtract 10 on both sides. We got 5x equals 170 divided by 5 on both sides. X equals, so we got 170 divided by 5. 5 goes into 17 3 times. And so you get 34 for x. And then we're going to plug this in to get all the angles. So we're going to plug this into here. So I plug it in there. I get 3 times 34 equals 128, or let's see, I get 12. So I should get 102 degrees. I plug it in there. And then if I plug it into this one, I get 78 degrees. So that's 78, this is 78 degrees, that's 102, this is 102. So we got all the angles for the parallelogram. Okay, so we got here, find x and y for the parallelogram below. So again, the opposite angles are congruent, so we can set those equal. Or yeah, we can set those two angles equal. And then we can add these up. So these two are supplementary. So we're going to add those up. Those are add up to 180 degrees. So I'm actually going to do that over here. Okay, so first thing what I'm going to do is I'm actually going to solve for y here. Solve for y here, and then I'm going to plug it into this equation, or solve for x. So I'm going to solve for x here. So I'm going to subtract 2y on both sides, and I'm going to subtract this x over here. So if I do that, I get x equals 2y. All right, so there you go. X is solved for. X equals 2y. Then I'm going to plug that in here. Well, before I do that, I'm going to combine my like terms here. So we got and combine these. So we got 2x plus 5y equals 180. Then I'm going to plug in x equals 2y into there. So we got 2 times 2y plus 5y equals 180. And then if I continue there, I get 4y plus 5y equals 180. We get 9y equals 180. Divide by 9. So y equals 20. So again, if I'm going fast, you might want to pause it or rewind it, just because I do want to do this in a timely fashion. So we're going to plug in 20 into, we want to find x and y, so we're going to plug it into x here. So if I do that, I get x equals 2 times 20, which is 40. Okay, so here's the bonus problem. So for the rectangle, so remember that in a rectangle, the diagonals are congruent. All of the diagonals are congruent, so we can actually set those equal. Now this is not going to be true if it's a parallelogram. These two diagonals will not be congruent for a parallelogram, but they are congruent in a rectangle, okay? The way they're situated here. So here we're going to set them equal and solve. So I'm going to subtract 3x, and then I'm going to move the 1 over to the other side. Divide by 2, x equals 5. All right, so then we're going to plug this into AC, but we know AE is 5x minus 1, okay? So we know that AE, so if I plug in AE, is 5x minus 1, so 5 times 5 minus 1, which is 24. And so AC is, so if this is 24, if this is 24, then this is 24, right? It has to be the same. So it's going to be 24 plus 24. So 24 plus 24 is 48. So AC is 48. Okay. So let's look at 1.5. Find the length of the mid-segment of the trapezoid. So remember the trapezoid mid-segment theorem states that if I have a mid-segment that divides a trapezoid in half, like this, where it connects the two midpoints rather, and it's parallel to the bases, then to find the length of the midpoint, I take the average of the two bases. So C is equal to A plus B divided by 2. Okay. So in this example, we're going to do this here. So we get x is equal to 10.7 plus 20.3 divided by 2, if you refer this to A as and B. So I add these together, I get 31 divided by 2, which is 15.5. So there's your length. All right, so the next one, we're going to do the same thing. So we're going to say this is equal to the average of these two. So this equals 9 plus 13 divided by 2. Well, 9 plus 13 is 22. 22 divided by 2 is 11. So this is equal to 11, and I can solve. I can move add 7 to both sides. So I get 18 divided by 3, and x is equal to 6. So we're going to plug this in to here to get the length of the midpoint. So we get 3 times 6 minus 7 is 18 minus 7 is 11. So there's the length of my mid-segment. And if you think about it, actually, I mean, we already knew that it was 11. So let's say find the length, and we'll put find x. Okay, so we don't just want to find the length of the mid-segment, we also want to find x. So make sure you include that in your question. So we already knew that it was 11, so because we said it over here. Okay, so I'm going to say this is 11, and x is equal to 6. Okay, so we'll say both of these are the answer. All right, so this one, we want to find the length of the base. The bases these are the two bases. So we want to figure out those two lengths. So we're going to, again, say this is A, B, and C. So it's C equals A plus B divided by 2. So C equals A plus B divided by 2. So in order to get rid of this 2, I'm going to multiply both sides by 2. And then I got to make sure to distribute. So I got 2 times 2x is 4x. 2 times 4 is 8. Combine my like terms here, that's 5x. Combine this, that's 3. Subtract 4x on both sides. Subtract 3 on both sides. So we get 5 equals x. And then I'm going to plug it in to get the base, to get both bases. So we get 3 times 5 plus 2 is 12. So that's one of my, 3 times 5 is 15. So this is 17. So there's my base for that one. And if I plug in this one, 2 times 5 plus 1 is 11. So those are my two bases, 11 and 17. Okay, so let's look at 1.6. Again, the 12-meter flagpole casts an 8-meter shadow. A tree casts a 20-meter shadow. What is the height of the tree? So these are two similar triangles. I want to make a note here that I didn't do in class. I want to show you why these are both similar triangles. Now, we know that because these two are heights, that these are actually parallel. and therefore these two angles are corresponding angles and they're congruent. We also know that these two, this angle is congruent to itself by reflexive property, right? And therefore the two triangles are similar by angle, okay? So these two triangles are similar. So therefore we can actually show that they're proportional. All right, so we can say that, okay, so 8 is to 20 as 8 is to 20 as 12 is to h. And then we can cross multiply. So we got 8h equals 20 times 12 is 240. Divide by 8, so h equals 30. Again, just be consistent. So if you use 8 for the top, then you must use 12 for the top, because it's for this you got to be consistent. You want to use the small triangle on the top or the small triangle on the bottom. You have to be consistent when you do it. All right, so for this one, you're going to try to find x, and then you're going to try to find the area. Okay, so here they said that y is 1.25. So we're gonna first, we realize that these are similar rectangles. So we said that 8 is to x as 20 is to 1.25. All right, so we set it up that way, and we cross multiply. So we get 20x equals 8 times 1.25 is 10. Then divide by 20. So x is equal to 0.5. So we know that this is 0.5, and then we can find the area. The area of a rectangle is base times height. So it's going to be 0.5 times 1.25. We're just multiplying these two sides here. And that gives us 0.625. I want to say that that's the area, but let's double check that. Times 1.25. Yeah, 0.625 is the area of the smaller rectangle. So this is the answer we're looking for. All right, so that takes care of that. Let's look at the next standard, or the next benchmark, GR 2.1. So for these two problems, I am not going to do the entire thing. I'm only going to do a couple of the coordinates, maybe 3. But remember that there are 5 coordinates for each of these problems, and doing all 5 coordinates is going to take some time. So I'm going to show you how to start the problem and do it, and then you can finish it. Okay, so for the first one, given the pentagon with the coordinates given, determine the coordinates of the vertices of the image after the following transformation. So you're going to rotate 180 degrees, and then you're going to translate using that rule. So let's write down the rules for rotation. For 180 degree rotation, the rule is that xy maps to negative x, negative y. So that's the 180 degree rotation about the origin. We already got the rule for the second one, so we don't have to write it. Okay, so let's go ahead and show you how to do this. So the first coordinate is w, which is 2, 2. So we're going to first rotate, so 180. So we're going to negate both coordinates. So it turns into -2, -2. Then we're going to follow that up by adding 5 and subtracting 2. Okay, so we're going to add 5 minus 2. So if I do that, that's going to be 3 and -4. So this is my w prime. So this is one of my answers. So now we're going to do the same thing for x. So if I negate both coordinates, I get -3, -5. And then I'm going to, again, do the same thing. I'm going to add 5 and subtract 2. So in other words, I get 2, -7. So this is x prime. Okay, and like I said earlier, I'm not going to do all the coordinates. You're going to do the same thing using those 2 transformations to get the rest of the coordinates. All right, so for this one, again, we're going to do this. We have the same coordinates, but this time with different transformations. So we're going to reflect about y equals -x, and then follow that up with a rotation 90 degrees. Okay, so let's write down the rule for the reflection about y equals -x. So if I want to reflect about y equals -x, I have to switch the coordinates and then negate. In order to do a rotation 90 degrees clockwise, I need to rotate, or I need to switch the coordinates and then negate the second coordinate, right? After I do the rotation, then I negate the second coordinate. All right, so that's my 9 degrees clockwise rotation. All right, so let's go ahead and do this for W. So W is 2, 2. So if I do the first transformation, I switch and negate. Then I switch it again, which again, it's going to look the same if I switch it because it's the same number. And then I negate the second coordinate, so I got to put another negative there. Well, if I put another negative there, this turns into positive, right? So it turns into positive 2. So there's W prime. Okay, so let's do X. X is 3, 5. So we're going to switch them and then negate. So you go -5, -3. And then we're going to switch them again and then negate the second coordinate. But it's already negative, so double negative makes that turn positive. So that now at this point you can see a pattern. The 2, 2 turned into -2, 2, right? And then you can see 3, 5 turned into -3, 5. So you can see that the pattern is I just have to negate the first coordinate, and that gives me the entire transformation, both transformations. Okay, so at this point you can shortcut it and say that, okay, Z is going to turn into -4, -3. Okay, so then you got your answer for Z. Okay, like I said, I'm not going to do the rest of them. Just use the same procedure to get the rest of the coordinates. All right, so here's the next one is 2.2. The vertices have the following coordinates. Under which transformation is the image not congruent to triangle JKL? All right, so for this one, it says determine if the given transformation preserves distance or angle measure. So for this standard, you need to realize that rigid motions, also known as congruence transformations, these are transformations that preserve, they preserve distance and angles. Okay, these are things like rotation, reflection, and translation. Okay, so if I rotate, translate, reflect, it's not going to change the shape. It's going to keep it congruent. All right, it's not going to change the distance, angle, anything like that. That's a rigid motion, or otherwise known as a congruence transformation. On the other hand, you have similarity transformations, right? So, I'm going to use the shortcut, the abbreviation, the similarity symbol. You have similarity transformations, all right? Similarity transformations. Now, these transformations preserve only the angle. Okay, so these are similarity transformations are dilations or dilations plus rigid motions. Okay, so it could be a congruence, it could be like a congruence transformation combined with a dilation. It's still going to be a similarity transformation, because if I do a dilation, it's going to change the size and it no longer preserves distance. So as long as you got a dilation tossed in there, this is always going to be a similarity transformation, and it's only going to preserve the angle but not the distance. Okay, so here they're saying you have a triangle. Which transformation is the image not congruent? So that means you have to do some kind of dilation. So this is a rigid motion, so this can't be the answer. Translation is a rigid motion. Counterclockwise rotation, rigid motion. Reflection, rigid motion. Dilation, this is my answer. Dilation is a similarity transformation. All right, so here it says you got a triangle DAB and it's reflected over the x-axis. Which is the reason that justifies why AB is congruent to CB? Well, AB is congruent to CB is because we did a rigid motion. We did a reflection, which is a rigid motion. It's a congruence transformation. And we know that when we do a reflection, distance is preserved under a reflection. So the answer is 1. Orientation is not preserved, meaning the direction does change. However, the distance is preserved. 3 and 4, although 4 is the right angle remains congruent under reflection, this is not the reason why these are congruent. So neither of the rest of them are the answer. So the best answer here is number 1. All right, so for number 3, under which transformation is the triangle not congruent? This is similar to the one that we did in number 1. In fact, it might be the same type of problem. Yeah, so it's going to be the same. It might be a copy. So the answer is D. All right, so here we go, GR 2.3. Describe a similarity transformation that maps the trapezoid to the PQRS to trapezoid WXYZ. So you're going from the blue to the green. So notice that this is a similarity transformation because the distance is not preserved. They got smaller, right? The distance is shrunk. So we need to do a dilation combined with some rigid motion potentially. And it looks like we're going to need to do a reflection. So I'm going to reflect across this axis. So if I reflect across the y-axis, I get something that looks like this, where this is Q, R, and then P is going to be here. Hold on, let me make sure. 1, 2, 3, 4, 5, 6. Yep, so this is P, and then go straight down. So this is how it's going to look like when I do that. Okay, and then I'm going to need to shrink it. So once I do. All right, so as my similarity transformation, I have, first off, I have a reflection across the y-axis. And then follow that up. So then next we need to shrink it, right? We're going to do a reduction. So how much do we need to reduce it? Well, if I look at here, this is 2. And here, this is 1, 2, 3, 4, 5, 6. So this is going from 2 to 6. The same thing here. This is going from 1 to 3. So the scale factor is 1/3, right? So the scale factor K is 2 over 6, which is 1/3. Which means, actually, yeah, we need to shrink it by 1/3. So we're going to divide it by 3, and that's going to shrink it so that it's 3 times smaller. Right? So we're going to do a dilation, and this dilation is from the origin. So if I shrink this by 1/3 from the origin, this is going to work. Okay, so dilation with center at the origin with a scale factor of 1/3. Okay. Okay, and so yeah, so this is the similarity transformation. This is going to get from this is going to make it so that the blue gets to map onto the green. Okay, so that's what we mean by similarity transformation. It consists of a rigid motion and a dilation in this case. All right, so here we got. So this one we need to actually draw it out. And then identify the similarity transformation. So we're going to show you how to do this using SSS SSS similarity. So I'm going to quickly draw this. Now I'm going to do this over here. Just well, yeah. So I'll go ahead and do it over here. So let's see here. I'm going to draw this out. Okay, so this is the image, and then we'll do the pre-image here. So -2, 2. We got -2, -4. Okay, so notice that in this, to get from the smaller triangle to this bigger triangle, we need to first line them up and then stretch, right? So to make it bigger. So what I'm going to do is I'm going to take G and I'm going to line it up with G prime. So I'm going to move it. So I'm going to be 1, 2, 3, 4. So I'm going to move it 4 to the right, and then I'm going to move it 1, 2, 3 down. So I'm going to do that for all of them. Okay. So 4 to the right, 3 down. So I'm going to do a translation along the vector 4 comma negative 3, and this is just saying that I'm translating 4 to the right and down 3. You can write 4 to the right and down 3. I just find that doing this translation vector is just a little bit easier for me. So translation along that vector. Okay, so again, if I do that for this, 1, 2, 3, 4, and then 1, 2, 3, I get to that point right there. Okay, so far we got G is here, H is here, and then this, if I move it down 3, oh, I'm sorry, not down 3, down 2, sorry. This should say negative 4, 4 to the right and down 2. So because G is over here, so I need to move it actually down 2, sorry, my bad. So 4 to the right, down 2. So if I do that, so here, 1, 2, 3, 4, 1, 2. So this is where F is going to end up if I move it, okay? So here, this is what this red triangle is, where they overlap so far. All right, so then next, notice that the length of this side is 6, and then the length of this side from here to here is 12. The length from here to here is 2, and the length from here to here is 4, right? So it looks like the scale factor is 12 over 6, which is 2. So the scale factor is 2. So we're going to double the length of this, right? So let me write it over here. 12 over 6 is 2. That's my scale factor, K. Let me write this, K equals. All right, so that means I need to double the length. So we're going to do a dilation. And this dilation is from, notice that it's from G prime. So the center is from G prime, and then we're stretching it to the rest of the triangle. So dilation with center G prime with scale factor of 2. Okay? So there's my similarity transformation for that one. So let's do the next one. So we got 2.5. Again, this is another pentagon example, and then they want you to graph it. I am not going to graph it. I'm going to just give you the coordinates, and then you can graph it yourself. Okay? I'm not going to, you know how to. Most of you guys know how to graph. So I'm not going to focus on the graph. I'm just going to focus on what the new coordinates are going to be. All right? So just so you're aware. Normally in these types of questions, you'll have to, like if you see here, it says determine which graph represents the transformed pentagon. So they're probably going to give you a bunch of graphs, and you have to pick the right graph anyways. So you won't even have to graph it yourself. You just figure it out. Okay, so here we go. So we are reflecting about x equals 1, followed by a translation by the given rule. Okay, so those are your two things. Now, if I want to reflect about x equals 1, I'm going to show you how to do that. So I'm going to do this for all, I'm going to do it for a few of the coordinates. I'm not going to do it for all of them. I'm going to do it for w, x, and z. Okay, and then you guys can do the rest. X is not 4, -3. Z is 4, -3. X is 3, 5. So I'm going to do it for 3 of them just to give you a couple of examples, and you guys can apply the rest. All right, so we got reflection about x equals 1. So here is x equals 1. So this line right here is x equals 1. It's a vertical line. Okay? And we're going to reflect 2, 2 across there. So we got 2, 2. So if I reflected, that's 1, 2, 1, 2. So it's going to go over here. So this is going to be the coordinate -1, comma 2. So that's going to be where it reflects. So we got here -1, comma 2, and then let's follow that up. But let's do the other coordinates first. 3, comma 5. So if I do 3, comma 5, let me erase this. Let me erase. Shoot. Let's see here. I'm going to try to erase just those things. Okay, here we go. All right, so let me make sure that this is, yeah, this is 2, comma 2, 1, 2, 1, 2. Okay. All right, so 3, comma 5. So 3, Oh, this is not 2, 2. This is 2, 2. Sorry. Over here. So this is actually incorrect. So this is going to be 2, 2 this is 1 space away. So it's got to be 1 space away over here. So it's actually going to be 0, 2. All right. So I apologize for that. 0, 2. I knew something was off about it. Okay. So now let's do 3, 5. So we got 1, 2, 3, 1, 2, 3, 4, 5. So this is 3, 5. So if this is 1, 2 spaces away. So it's got to be 1, 2 spaces away there. Okay. So the coordinate is going to be -1, 5. All right. So we got -1, 5, and we'll do one more for this one, 4, -3. So 4 and then -3. That's not 4, -3. That's 5, -3. 1, 2, 3, 4. This is 4, -3. So we got 1, 2, 3, 1, 2, 3. So you're like over here. So it's -2, -3. All right. So there is my coordinate. So -2, -3. All right. So that's how we do this part. And then the next thing we're going to do is we are going to use this rule right here. So all we're going to do is we're going to subtract 2 from the y coordinate, and this means that we're shifting the graph down 2. Okay, so all we're going to do is do -2, -2, -2 for all these. It'll be 0, 0. This one is -1, 3. This one's -2, -5, so on and so forth. Do it for the rest of the coordinates, and then make the graph. Okay, so here we go. We got the coordinates of the rectangle. So we got a rectangle, and we want to graph the image under a 270-degree clockwise rotation, followed by a reflection about y equals -x. We did the rule for reflection by y equals -x, but I'll remind you again how that works, just in case you forgot. So if I rotate 270, that is going to, you're going to need to switch the coordinates and then do and then make the first coordinate, negate the first coordinate. And then again, just to remind you of the reflection about y equals -x, we switch the coordinates and then negate both of them. So again, I'm going to just show you how to do just a few of them, not all of them. I'm just going to do 2 of them. Okay, so let's do the first one and second one here. Okay, so we got, so if I switch the coordinates, this turns into 1, -3. Then I'm going to negate the first coordinate, so that turns into -1. And then if I do that, I get, then I need to switch the coordinates again, and then I'm going to negate both of the coordinates. But if I negate both of these both turn into double negatives, which makes them turn into positive, okay? So I'm going to turn them both positive. Okay, so this is going to be A prime. We'll do one more. So for B, we're going to switch the coordinates and then negate the first coordinate. So there you go. So it's -1, 2. And then we're going to follow that up by switching the coordinates again and then negating both of them. But if I negate the first one, that turns negative. If I negate the second one, that becomes double negative, which is a positive. So these are my 2 coordinates, okay? And then go ahead and apply the same process for the next one. Now you can see that the pattern here is that this is going to be, you just negate the first coordinate, right? You can see that pattern there. Okay. All right, so let's look at the next problem here. So next standard, we got GR 2.8. Here, select which transformation will map one triangle to another, and then which will map one pentagon to another. I didn't give you a pentagon problem because, you know, it's just an extra 2 points. So it really doesn't make that much of a difference whether you have 3 points or 5 points. It's actually just more work if you have 5 points. However, you know, doing a couple triangle problems will still get you prepared for doing a pentagon problem. So we're not too worried about it. So this is similar to what we did earlier on one of the other things. We're going to do a similarity transformation. So again, if I take E and I move it to U, we're going from the blue to the green. So we're gonna need to line them up and then stretch the blue out to get to the green. So we're gonna move this to the right one and then down one. Okay, so as first part of my transformation, I'm gonna translate one to the right and one down. So I'm gonna translate along this vector. This means you're going to the right one, you're going down one. You can put this in words. You can say translate one to the right, one down. And then if I do that, well then E is going to be here, and then D is going to be here, and then E or F is going to be here. Okay, so this is going to be where the triangle ends up, this red portion here. And then if you notice that this length is 4 and this length is 8, this length is 2, this length is 4. So the scale factor here is K equals 8 divided by 4, which is 2. So we need to double the length of it. So we're going to do a dilation. And this dilation is with the center at U, okay? Dilation with center U with a scale factor of 2. There's my similarity transformation. Similar to what we did, no pun intended, similar to one of the previous problems that we did. All right, so determine whether the two polygons with the coordinates given are similar. So we're going to graph this, and then instead of doing the similarity transformations where I transform it and all that, what I'm going to do is I'm going to show that they're similar by using SSS similarity. So let's do that real quick. So let me go ahead and graph these. Okay, so here we got A is 6, 0. Got B is 9, 6. C is 12, 6. So there's my triangle, and then we're going to compare that to D, which is 0, 3. Okay, so very small triangle compared to this bigger triangle, okay? And so we're gonna compare them and see if they're similar. So here, the length of this is a length of 1. This is a length of 3, okay, from here to here. And then we're going to figure out what this length is over here. So if I count this here, 1, 2, this is 2, and then this is 1. And then if I count this length here and here, this is 2 and 2, okay? Now if I count here and here, this is 6 and 6. If I count here and here, this is going up 6, this is going over 3. Okay, so now if I compare these, I can see that 1 and 3 have a scale factor, that's a scale factor of 1/3, right? And then if I compare this 2 with this 6, well, that's a scale factor of 1/3. So that looks good. If I compare, again, similarly, if I compare these two, 6 and that 2, scale factor of 1/3. If I compare this with this, scale factor of 1/3. This with this, again, scale factor 1/3. So the scale factor is 1/3 everywhere. So that means by SSS inequality, or by SSS similarity, sorry, that these two triangles are similar. So similar by SSS similarity, okay? The scale factor is the same everywhere. And you can do it that way pretty easily. All right, so GR 3.2. Given the coordinates for the vertices of a square, determine which set of steps prove that the diagonals of the square are perpendicular. So what we're going to do is we're going to first, oops, let me go back, sorry about that. What we're going to do here first is we are going to prove, or we're going to draw the square, and then we're gonna show that it's a rhombus by showing that the diagonals are perpendicular, and then we'll go back and show that it's a square. Okay, so that's what we're gonna do. We're gonna kind of bounce around. Okay, so let's go ahead and first graph this. Now this is gonna be obvious that this is square, but remember, it's not always gonna be obvious. So I'm gonna show you how to do it regardless of how the shape might look like. This is, by the way, -2, -5, all right? So the 5 went on the bottom, but there's this negative right here, okay? And then h is -7, -5. So again, like I said, this is very obvious that it's that it's at least right angles, okay? So we got E, F, G, H. And it's easy to show that it's a square, but like I said, we are going to show it a different way because just in case it's not as obvious in the future, right? So what we're going to do is we're going to first show that this is a rhombus. Remember, for something to be a rhombus, you have to have a parallelogram where the diagonals are perpendicular, okay? So this is for a rhombus. So rhombus is a parallelogram where the diagonals are perpendicular. And we also know that for a rectangle, we know that it has 4 right angles, but we also know that the diagonals are congruent. The diagonals are the same length. So, and we know that for something to be a square, it has to be both a rhombus and a rectangle, right? Rhombus plus rectangle. So we're going to prove both of these, and then that's going to show that it's a square, right? So let's prove that it's a rhombus by showing that the diagonals are perpendicular. Why am I so focused on the perpendicular? Well, look over here. It says determine which set of steps prove that the diagonals are perpendicular. So we need to show you how to do that because that is what they're going to be focusing on for this standard, okay? This is why I'm focusing on that. All right. So first off, let's draw the diagonals for this. We got the diagonals are EG, HF. So we need to show that this is perpendicular. That's what we're going to do right now. EG and HF. To show that they're perpendicular, we need to find the slopes, okay? So notice that if I count these, this is the slope for EG is, well, it looks like 1, 2, 3, 4, 5, right? So this is rise over run, right? So it's going down 5 and over 5. Okay, so down 5 over 5. Now, so that's going to be EG. Okay, so let's do the slope for EG. Slope for EG is rise over run. So -5 over 5, which is -1 over 1. Now we're going to do the slope for HF. Okay, so again, the slope for HF is going to be, let me do this in red. So rise 5 and run 5. So we get 5 over 5, which is 1 over 1. All right, so notice that these are perpendicular because they are opposite reciprocals. If I flip that, I get the second fraction, and they're also opposite signs. So these two are perpendicular, okay? So EG is perpendicular to HF. So therefore, there's a 90-degree angle, okay? So we haven't shown that it's a rhombus yet, okay? So in order to prove that it's a rhombus, we also have to prove that it's a parallelogram, okay? So, but we've at least shown that this is a right angle. So this is good. I can go ahead and confidently say that that's a right angle. Now I've got to show that it's a parallelogram. Is it a parallelogram? Well, it's easy to tell because we can see that EF is parallel to HG and EH is parallel to FG, okay? We can see that because they're both parallel, or they're both horizontal and vertical lines. So we can see that EF is parallel to HG. I used the wrong symbol here. EF, there you go. And then EH and FG. And EH is parallel to FG because they're vertical and horizontal lines. Okay, so therefore it is a rhombus. Okay, so proving that it's a parallelogram and that the diagonals are perpendicular means it's a rhombus. Now, since we've proven that it's a rhombus, let's go ahead and prove that it's a rectangle. We're going to prove that the diagonals are congruent. This is easy to do because we know that this is 5 and this is 5, right? So that means FH is equal to the square root of 5 squared plus 5 squared. And then we know that this is 5 and this is 5, so EG is equal to the square root of 5 squared plus 5 squared. They're literally the same thing. So this is square root of 50 and this is square root of 50. So it's showing that FH is congruent to EG. So the diagonals are congruent. So these are all congruent, which means that we have a rectangle, okay? Since it is a rectangle, and this shows that it's a rectangle right here, this property. Since it is a rectangle and a rhombus, again, it's a rhombus from this side here, it must be a square. All right. Okay, so like I said, obvious that this is a square, but we're showing you how to do it in terms of the diagonals. All right, so let's look at GR 3.3. Here, given the coordinates, determine the fourth coordinate. So given the coordinates for the 3 vertices of a trapezoid, determine the fourth coordinate. Okay, so we're going to graph this. So let's graph it real quick. Let's see, so we got 1, 2. So this is A is 2, 0. B is 0, 2. C is 0, 7. And what I'm going to do is I need some room, so I'm going to move this down. Okay. All right, so we got, and then D is somewhere around here, but we don't know what D is, right? D is a question mark. We need to figure out what D is. But we know that this is an isosceles trapezoid. An isosceles trapezoid is a trapezoid where the two sides that are not parallel are congruent. Okay, that's what makes it isosceles. So so that means that this has to be the same length as this. Okay, so which means that if I count this is 2 and 2, that this has to be 2 and 2, right? Well, we know that this is at 7, right? So 7 plus 2 is 9. So this is actually at 9 over here. And then, so the coordinates of D must be 9, 2 if I count it. And that is it. That's how you find the fourth coordinate of D. This is the easiest way to do it. Graph it, and then notice that these two have to be the same length. And so for this to be true, we can figure out, we can just count up and over should be the same amount, okay? And that's how you find D. That's a really quick way of doing that. And there's only one problem on that I was able to find. All right, so here we go, 4.5. Find the volume of a given pyramid. Okay, so here we go. We find the volume of a given pyramid. So so here we need, the first one, we need to find the volume of a pyramid, but we also need to find the volume of a cone, okay? So again, we're going to show you how to find this on the formula sheet. So let's show you the formula sheet. This is the formula sheet for the EOC, right? Let me see if I can show you. Okay, so here we go. Yeah, this is at least one of the sides. So here, this is like the back side of the sheet. But if you look here, we have the formula for the cone, right? And we have the formula for a pyramid, okay? So notice that the formula for the volume is the same as 1/3 BH. All right, so we're gonna write that formula down. We also know that B is the area of the base, okay? So remember that the area of a cone, or the base of the cone, is a circle. So we need to figure out the area of the circle for the cone. Well, the area of the circle is pi r squared. All the formulas are given there, but you just have to know how to find them. So we're gonna plug this into this formula, pi r squared, okay? All right, so let me do that. Let me do the cone first, and then we'll go from there. So volume of cone, 1/3 BH, but then B is pi r squared and H. We just got to plug it in. 1/3 pi times the radius is 7 squared, and then the height is 28. So there's my volume of my cone. Now we're going to do the volume of the pyramid. Same formula, 1/3 BH. But this time they said that the base area of the pyramid, they're saying that that base area is 154. So they actually already give you this. That's the base area. And then they said that the height is 28, right? So 1/3 times 154 times 28. Okay? So there it is. And then we're going to figure out which one is bigger. So we're going to figure that out now. So let's do that over here. So we get 1/3 times pi times 7 squared times 28. All right, and then we get for the next one. So we get, they're pretty close, 1,436, 1,437. So it looks like the solid with the greatest volume is the pyramid by a short amount, by a small amount. So we got, this is approximately 1,437, this is approximately 1,436. So the pyramid is greater. All right, so hopefully that helped. So now let's look at the second one. This one's the volume of this is another pyramid. So we're gonna say that this is the base of the pyramid, okay? So remember the volume is 1/3 base area times height. This is the height of the pyramid is 4. The base area, so the base is a triangle, right? So it's this triangle right here where we got 3, 4, and 5. Now it's important to note that the area of a triangle is not given in this formula sheet. It's not, okay? So it's imperative that you remember what the formula for the triangle is. It's not hard to memorize. So please memorize the formula of the trapezoid or the triangle. Or you can realize that they give you the formula for a parallelogram. So if they give it to you for a parallelogram, then you know that's the same thing as a rectangle. That's the area of a rectangle. And you just realize that there's 2 triangles that fit in a rectangle. So a triangle is simply going to be half of the area of a rectangle, okay? So in other words, the area of a triangle is 1/2 base times height, okay? So remember that or you're gonna have trouble. So the capital B here is 1/2 little b little h. Remember also that the base and the height are perpendicular to each other. So they have to be at a right angle, okay? So this is your B and this is your H. So remember it's not 5. You're not gonna use 5 in this calculation. All right, so we got 1/2 times 3 times 4 times 5 times 4 times 3, sorry. So this is gonna give you 6. All right, so the base area is 6. So 1/3 times 6 times 4. So we get 2 times 4 is 8. So it's going to be 8 cubic miles. All right, so it takes care of the second one. Now let's look at the third one. So the base is a rectangle. So we're going to find the base area from that. So remember the capital B is the area of the base is of a rectangle is base times height. So little b, little h. So it's 5 times 2, which is 10. Remember the formula for a pyramid is 1/3 base area times height. And this is the height. So we got 1/3 times 10 times 5. 5 times 10 is 50. So you got 50 over 3. You can 50 divided by 3, which this is a decimal, so you can leave it like that. This is the volume. All right, so that takes care of that one. So we are wrapping this up. We got, so we got about 3 more standards to go. Okay, so here we have we want to find the surface area of a sphere. So let's go ahead and go to the formula sheet, figure out what the surface area of the sphere is. Surface area of a sphere is 4 pi r squared. Okay, pretty simple. All right, so here we go, 4 pi r squared. So surface area equals 4 pi r radius squared. So find the surface area of the Earth. Okay, so 19, the surface area of the Earth. So surface area, and it says that the radius of the Earth is 3,960 miles. So we're going to use that for the radius. So 4 pi times 3,960 miles squared. Okay, so we're going to multiply that to get the surface area. We'll multiply that in just a little bit. Now we're going to do the surface area of the moon. So 4 pi times 1080 squared. And we got we got the surface area of the moon. Okay, so let's figure out what those two numbers are. Do that right here. Okay, so we got here, remember that this, okay, so remember that this here is saying you're moving the decimal place 8 to the right. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's what this e times 10 to the 8th power is. So we got 197060797.4. We're just going to round it to 0.4 because this is where the decimal goes if I move this 8 to the right. Okay, so it's a big number. So we're gonna round it to just do they want us to round it? It doesn't actually specify. So we're gonna round it to the nearest whole number. So we get 197,060,797 square miles. Okay, so that makes sense based on how big the Earth is. So we're gonna write that. So 197 million 60,000 797 square miles. So miles squared. And then we'll do the same thing for the moon. So again, move this. This is times 10 to the 7. So 1, 2, 3, 4, 5, 6, 7. And we're going to bump it up because this is a 6. So we're going to bump that up to a 5. So 1, 4, 6, 5, 7, 4, 1, 5. All right. So that's going to be 146 million, or no, 657,415 square miles. Okay, so if you notice that there's a big difference between the square mileage of both of them, which makes sense. Based on the size of the moon and the Earth. Now we're going to compare the surface area. So to compare the surface areas, we're going to divide these. So we're going to say we're going to do the surface area of the Earth. We're going to divide it by the surface area of the moon, and then that'll tell us how much bigger it is, okay? So we can divide those. I'm actually going to divide these two numbers here. I'm going to copy this number. Well, actually, no. I'm just going to do the numbers that we wrote down, okay? Okay, so we got that. Divide that by 14,657,415. We'll divide that, see what we get. Uh, 415, okay. So we get about 13.4, okay? 13.4. So we get that the surface area of the Earth is about 13.4 times greater than that of the moon. Okay? Way bigger. However, remember that the surface area of the Earth, the entire Earth, most of the Earth is ocean. So 70%, around 70% of that surface area is actually just water. So how does it compare if it's just land, right? So that's something to keep in mind. So that's 30% is land. So we do 30% of this 197 million number, and that tells us the actual usable surface area that we can walk around. Of course, the rest of the surface area is there for navigation in the seas, right? But for actual walking around. But for number 22, it says 70% of Earth's surface is water. How many square miles of water are on the surface? So we're going to do 70% of this number, okay? So I'm going to do 70% of that number and you get an answer. So I'm gonna leave it to you guys to multiply that. I'm not gonna do that out. Just do 0.70 times that, and that'll give you the surface area of the water on the Earth. Okay. All right, so that takes care of that standard. So we got the next one is 5.1. Okay, let me go back here. Okay, so here we just want to identify the construction, determine what construction it represents. All right, so and this one's asking what's the next step in the construction. So I'm going to show you the steps in the construction. So the first thing you want to do is you want to draw the ray, which we have here. So you draw the ray, and then using the compass, you're going to draw an arc on both of these. Okay. Then you're going to use the compass to measure the distance between here and here, and then use that distance to mark from here to here and draw an arc. And then this distance here that we measured is got to be where you connect this here. Okay, and that's how you copy the angle. So those are all of the steps. So if we answer the question, what's the next step? Well, the next step is to label these points and then measure that distance. Okay, so part A, continue drawing the circle. No. Label the points where the arc intercepts. That looks good. Draw another arc of a different size. No. Use a straight edge to draw the bisector. Definitely not. So the answer is B. Name the construction. This is exactly what we did here, this construction, which is constructing an angle. So we're constructing the copy of an angle. All right, next one, when copying the line segment AB. So again, let me show you the steps here. This is AB. And the first thing you're going to want to do is draw a nice long line using a straight edge. Then you're going to use a compass to measure from here to here. Then using the same measurement on the compass, you're going to start from here and then draw an arc here to mark out what the measurement is, and then you go from here to here, and this is your line segment, which is the same distance as that. So here, when copying a line segment using a straight edge, the compass should be used to do what? Well, the compass is used to do the measurement. Draw an arc above point A? No. Draw an arc between point A and B? No. Measure the length of segment AB? Yes. Okay. All right, and then the last one, this should be one more, right? Yeah, okay. Keep in mind that this is the standard is to judge the validity of arguments and give a counterexample. Two of these examples don't actually fit this concept. However, the last example does. Okay, so I just want you to keep that in mind. The first one, statements 1 and 2 are true conditional statements. If a figure is a square, then it is a rectangle. If a figure is a rectangle, then it is a parallelogram. What can we conclude? All right, so let's say this is P, let's say this is Q, and let's say that this is R, parallelogram. So the first statement says that P implies Q. The second statement says, well, this is a rectangle, so this is Q. So the second statement says that Q implies R. Well, that means that if P implies Q and Q implies R, that means P implies R. This is known as the law of syllogism. We did this in chapter 3 in the beginning of the year. I know a lot of you guys probably forgot that, but that's what the law is called. So it's sort of like the transitive property, but for logic, for conditional statements. So, all right, so in other words, if it's a square, then it must be a parallelogram. If a figure is a square, then it is a parallelogram. A, that's true. All right, so here, determine whether the conclusion is valid based on the given information, right, valid or invalid. Okay, so if a figure is a square, then it has 4 right angles. So P and Q. So P implies Q, and then it says figure ABCD has 4 angles. Can we say that it's a square? No, this is invalid. We can't go backwards. We can only go from P to Q. We can't necessarily go the other way around. All right. So yeah, so remember for this conclusion to be true, they have to tell you, okay, well, they have to say, oh, it's a square, and if it's a square, then it has, or no, sorry, yeah, if it's a square, then it has 4 right angles, but it doesn't work. It doesn't work backwards. It says you have 4 angles. That's not going to determine whether it's that it's a square. Okay, it only says that it has 4 angles. So invalid. If it has 4 angles, this doesn't make it a square. it makes it a quadrilateral. Okay, now a square is a quadrilateral, but not all quadrilaterals are squares. So this is going to be invalid in general. All right, so number 7, this is a true question that follows that standard, the concept that this says here. So it says, which figure can serve as a counterexample? If one pair of opposite sides of a quadrilateral is parallel, then the quadrilateral is a parallelogram. So we know that this is false because for it to be a parallelogram, you have to have 2 pairs, right? So 1 and then 2 pairs of parallel. If it has one set of parallel sides, that makes it a trapezoid, right? Because remember, a trapezoid only has the one set of parallel. So the answer is trapezoid. Trapezoid is the counterexample to this statement. All right, guys, that should be all of the questions. I hope you guys found this useful and informative. As usual, I'll see you in the next one.